Okay, so for this section, we're going to be talking about inverse trig functions again, but instead we're going to be talking about integrating trig functions. So last time we were talking about differentiating them, finding the derivatives. Now we're going to be talking about finding the integral. So let's see. In the objectives, we're going to integrate functions whose antiderivatives involve inverse trig functions. We're going to use the method of completing the square to integrate a function. And we're going to review the basic integration rules involving elementary functions. Okay, so first we'll look at integrals involving inverse trig functions. So on the last pair of slides, batch of slides, we were looking at the derivatives of all the 6 inverse trig functions. On this slide in particular, there's 2. As you can see, we look at the derivatives of arcsine and arccosine. Notice that they're very, very similar. Just the difference is, if you look at arccosine, when you take the derivative of arccosine, it's simply just the same as the derivative of arcsine, but with a negative sign in front. Okay. So, and then they all pair up like that, like cosine inverse pairs up with sine inverse, cotangent inverse matches up with tangent inverse, and then cosecant inverse matches up with secant inverse. So when we talk about the so like I said, they all pair up, and so when we look at that, the one we looked at before, it's better for us, rather than trying to remember both formulas, just remember that when we take arccosine, derivative of arccosine, that it matches up to the same as arcsine, but it has a negative sign instead. Just like whenever you would take the derivative of cosine, it goes back to sine, but it puts a negative sign in front. So it's very similar in that regard. So it's better to use arc sine of x as the antiderivative of 1 over square root of 1 minus x squared, rather than labeling it as minus arc cosine. And so these are just some indefinite integrals. So for the first one, we have the integral of 1 over the square root of a squared minus u squared with respect to u. It's just going to be equal to arcsine of u over a plus c. Then we look at the second one, where it's the integral of 1 over a squared plus u squared is equal to 1 over a with respect to u is equal to 1 over a tan inverse of u over a plus c. And then we have the third integral, which is the integral of 1 over u times the square root of u squared minus a squared, which is 1 over a arcsecant absolute value of u over a plus c. And keep in mind, we're looking at these for all a greater than 0. So for a, if we look at different examples, we're taking the integral of 1 over square root of 4 minus x squared with respect to x. Keep in mind, we have the x squared right here. We know it looks like the inverse sine function when we integrate it. The hardest part is really figuring out what our a is. And we know this is a squared, so we have to figure out a number such that when we square it, we get 4, which in our case would be 2. So when we follow the formula, it's sine inverse of x over 2 plus c. For the next one, this one doesn't have a square root on the bottom, so we know it's going to be an arctan kind of formula. The way we can do this is, first we want to be able to note that this part right here is going to look like 3x squared, and then we want to be able to take the square root of this, and so we get square root of 2 squared, because we want the square plus square on the bottom. And then remember, whatever this is in front of the x, we want to have on top, because that's how directly to the arctan inverse. So then putting the 3 on top means we have to also divide by 3. So multiply by 3 means we have to divide by 3, so we don't change the value. But the bottom 3 we can bring out, so then we have like 1/3 times that integral. And so when that happens, that's just going to be equal to 1 over 3. Remember, this is where the a goes, 1 over a, but then the 1/3 was already there, so we multiply those together. It's 1 over 3 square root of 2 And then arctan, remember the a was 3. The a was square root of 2, and then this was what our squared variable was. It was 3x. So it's 3x over square root of 2 plus c. And then for our final one, we look and we see we have x down here, and then we have a 4x squared down here minus 9. We want this x to look like whatever this variable is when we square it. So this variable on the inside when we squared it ended up being 4x squared. So the variable that we have is 2x. So we want this to look like a 2x. So then we multiply this by 2, but to keep the value the same, we multiply the top by 2. The 9 is just 3 squared. So we identify our u as 2x and our a as 3. And then we're able to just use our integral formulas to see that we get our a was 3, so we get 1/3. And then arcsecant of 2x, absolute value of 2x over 3, and then plus c. Okay, next we'll look at being able to complete the square to be able to solve these integrals. So, as you know, completing the square usually helps us to be able to solve different quadratic formulas. Completing the square can also be used to whenever we have certain formulas in our integral such that they're not quite as complete as we'd like for them to be. So that's where completing the square will come into play. Okay, and just to kind of review, so when we complete the square, we have x squared plus bx plus c. Then we have to add a b over 2 squared. This is where our complete square comes from. And then, of course, we have to subtract that same value just so we don't change the value of the equation itself. So then these 3 first terms, you can reduce that to x plus b over 2 squared. And then we're just left with the minus b over 2 squared plus c. So now, for example, we're looking at completing the square of x squared minus 4x plus 7. So note that when we're completing the square of the denominator, we can, so note to figure out what the number is we have to add is we're going to take the b, divide it by 2, so we get minus 4 divided by 2, which is minus 2, and then we're going to square it, so we get 4. So we're going to add a 4, and we're going to subtract a 4. Okay. When we add the 4, this right here, we're going to complete the square, so we're going to reduce this, and it turns out to be x minus 2 squared, or simplified if you will, and then the resulting on the outside is minus 4 plus 7, so that just equals plus 3. So then when we get ready to do our thing, we have our u squared, so our u in this case is x minus 2, and our a is going to be square root of 3. So then we know that u is equal to x minus 2 and a is equal to square root of 3. So we're able to see that when we just rewrite the integral using our complete the square formula. And then we know that there's no square root on the bottom. So we know it's going to look like arctan. Our a was square root of 3. So then we have 1 over square root of 3. And then our u is x minus 2 and our a is square root of 3. So we have 1 over square root of 3. Tan inverse of x minus 2 over root 3. And then, of course, our plus c. So we're just going to review some basic integration rules. Just kind of like how on the last batch of slides we reviewed the differential rules. This is pretty much the same idea, but only with integration. And we're assuming for any of our ones that involve an a that our a is greater than 0. So remember, whenever you're taking the integral of a function that has a constant in front of it, you can always bring the constant out. Remember, when you're taking the integral of functions that you're adding or subtracting, you can take the integral of them separately and then add or subtract the integrals depending on what you were doing before. Remember, the integral of just du itself is just u and then plus c. This integral is just the opposite of the power rule. So if you have u to the n, then you add n plus 1 and you bring that on the bottom, and it's easy to check that this is the derivative. Just take the derivative of this and you should get back to un. But this only works if n is not equal to minus 1. And of course, if n is 0, then we're left back with something like this. So du over u. So 1 over u. The integral of that is ln of absolute value of u. Just depending on what your bounds are, what your bounds were for u. It helps to use absolute value, because if you don't want to use, if you're using negative numbers, you can't take the ln of a negative number, so you have to include this absolute value. See, we have absolute value of the the integral of e to the u. It's just e to u and then plus c, of course. And then we have our other exponential functions when a is not equal to u, but of course remember we're assuming that a is positive. So the integral of a to the u is just 1 over ln of a times a to the u, and then of course plus c, and then of course sine goes back to minus cosine. And then of course we have a few different other rules, the other trig functions, as you can see, the ln's. As you can see, we have cosecant goes back to minus ln of cosecant u plus cotangent u. We have secant squared, which of course goes back to tan u. And then of course, once we get through all these, we go to our inverse functions. Now notice that when we were taking the derivative of these different forms, we only have 3 of them, because then, like, remember we said arc cosine. Remember, the one that's arc cosine, it would just have a negative sign in front. So then negative, rather than trying to remember that, oh, the negative goes with arc cosine, you can just bring the negative sign out of the integral and then just remember that this is for arc sine. So now you're only in a position where you really only have to remember 3 of them as opposed to all 6. So just those little shortcuts. This is the same idea with tangent and cotangent, and the same idea with secant and cosecant. So you want to be able to, based on the stuff we've learned so far throughout these slides, the question is, can you figure out, and not even just these slides, but things you've done before, can you figure out the integral? What techniques would you use to figure out these integrals? And so if you look at A, for example, A is a distinct example. It fits the Arcsecant rule. So you would just use the formula for the arcsecant to see that it's just that derivative, that integral is just the arcsecant of absolute value of x plus c. You get to B. If you notice that you can bring the 1/2 out, and you can sort of rewrite everything. So what you can do is multiply this by 2, but then also bring out a 1/2, so the value doesn't change. And notice that you can rewrite this bottom part as x squared minus 1 to the negative 1/2, but then notice that you have a 2x out here. So when you take the derivative of just this inner part, oh, you get 2x. So you're able to, you can use the power rule, which also would include u substitution as well. And so that's where you get, that's how you get the fact that this 2x is here. And then that just ends up being x squared minus 1 to the 1/2. You add 1 to this, and then you bring that new power down here, and then you plus c. And then of course you can see that one. This basically says you're going to multiply something by 1/2 and then divide it by 1/2. So the 1/2s essentially cancel out, and you're left with square root of x squared minus 1. Again, that's what the 1/2 means, and then it's just plus c. And then if we look at C, we actually do not have a formula for this one. Just because, keep in mind, when the integral that we have for this one, when we were looking at arc sine, the one for arc sine had a squared minus u squared. So the fact that this has x squared minus 1, that the labels are flipped in a sense, we actually do not have a formula for this one yet. So. And that's the end of that one. Hope the videos helped. If you have any questions, feel free to let me know. Comment on the video if you have any suggestions, or you can email me directly. My email's, so feel free to let me know if you have any questions. All right, thank you.